Hi. Last time we started discussing problem number 335. And I will finish today this problem. So number 335. It says a cyclic process depicted on a volume temperature diagram, and in such a way the cyclic process starts at point 1, and then the state of the gas is changed in such a way that the temperature increases from T1 to T2, and the volume also increases from V1 to V2, and so the gas is transferred from point 1 to point 2. Point 2 is another state of the gas. And then under constant volume, the gas goes to the state number 3, and then under constant temperature, the gas returns to the original state, which is depicted by point 1. And in these problems, we have two different questions. First question, show the same process on the PV diagram. So we have already done it. We did it last time on the PV diagram. In order to answer this question, you have to use the gas equation of an ideal gas. And I will take the equation for 1 mole. The number of moles is 1. This problem doesn't specify the number of moles, so I can take any number of moles, and I can consider for simplicity only 1 mole, and I will be sure that all other moles of the same gas will obey the same procedure and the same laws. So if we have volume in the process 1, 2, the gas volume is directly proportional to the gas temperature. If you see here in this equation, if volume is proportional to temperature, then pressure is constant. It means that the initial pressure in state 1 remains constant while the gas is transferred to state 2. That will be the line showing process 1, 2 on PV diagram in pressure versus volume diagram. The pressure must be constant during this process. Why do we know it? Why do we know that? Because of the equation of an ideal gas. If volume is proportional to temperature, and volume is actually proportional to temperature on this diagram according to the statement of the problem, then pressure must be constant. And we just indicate this process here. And another thing we have to take into account, what is the change in volume? That was volume 1, and that was volume 2. There are two possible ways to move along the line of constant pressure. The first possibility is to increase the volume, to go to larger volumes, and the second possibility is to decrease the volume, to go to smaller volumes. What is the case here? When we move from point 1 to point 2, volume is obviously increasing from V1 to V2. So we move on this diagram, we show the process going in the direction of increased volumes. And then process 2 to 3 goes under constant volume. Constant volume here is very simple. It goes along this curve to point 3. And again, we pay attention to the direction of the process. Here it goes from point 2 to point 3. The direction of the process at constant volume is such that the temperature of the gas decreases. The temperature decreases from T2 at the second point to original temperature T1 at point 3. So the temperature must decrease. and the temperature will decrease under constant volume if temperature is decreased, if pressure is decreased. So under constant volume, if temperature goes down, then pressure goes down. And we show this direction when pressure goes down, not up. And the process 2 to 3 should be directed downward in this diagram. And then the last section, 3.1, goes under constant temperature. The temperature of the gas here is constant and equal to T1. So if temperature is constant, then PV is constant. This quantity, the product of pressure and volume, must remain constant in this process. And we know that when PV is constant, the curve on this diagram, PV diagram, should be presented by hyperbola. This is a section of hyperbola. The hyperbola may go further, but we use only the section of hyperbola from point 3 to point 1. That is the answer to the first question in this problem. Show the same process on the PV diagram. Yes, we have shown it, the same process. So this diagram and this diagram refers to the same cyclic process with the gas. But here this process is shown in variables, in certain variables, volume versus temperature. And here the same process is shown on the diagram, pressure versus volume. And we were able to switch from one diagram to another diagram only basing on only using the ideal gas equation. No more information is needed. Just use the ideal gas equation and you will be able to show the same diagram in any axis. Volume versus temperature, or pressure versus volume, or pressure versus temperature. It's also possible to show this cyclic process in a diagram, PT diagram, pressure versus temperature. So another question here indicates the stages when the gas received and when it released heat. So on some sections of this process, the gas received heat from the outside bodies, and on another sections, the gas released heat. The heat was transferred from the gas to the outside bodies. And we have to find where the heat energy was transferred to and from the gas, on which sections of this diagram. In order to answer this question, we have to consider heat energy and heat energy transfer. So if we have some amount of heat energy, how can we understand what happens in this case? We must imagine a cylinder and the gas under piston, some gas under this piston, and the gas has some volume and it has some pressure inside it and some temperature, and the piston can move up and down. It can freely move in any direction, and the gas pressure will always act on the piston with some force directed upward, because the gas wants to expand and it's acting on the piston with the force, with such a force. If we want the piston to be at rest, we must exert equal force to balance the gas pressure and to keep this piston on its place, so that it would not move. If we don't want for the volume of the gas to change, we have to fix the position of the piston. That is, we have to act with equal and oppositely directed force downward in order to balance the force directed upward from the gas, from the gas pressure. So what happens if we convey some amount of heat energy to this gas? So we have we convey some amount of heat energy. That is, probably we use some heater from here, or some fire probably to convey heat energy to increase the temperature of the gas. What happens? First of all, the gas temperature may change. Surely, yes, in general case, the gas will be heated and the temperature of the gas will be increased. What does it mean that the gas temperature increases? It means that the internal energy of the gas increases. So the heat energy will go to increase the internal energy. I will use this notation for internal energy. Internal energy of the gas. The energy, the heat energy transferred to the gas, in general case, will change the internal energy of the gas. But that's not all that can be observed here. Also, the piston may go up if we allow it to go up. And the piston, if the piston goes up, then the gas pressure will perform some work. And when work is performed, we need energy. And this is maybe the result of heat energy. So if heat energy is transferred, then the gas performs some work. That is the work performed by the gas. What is written here is just the law of conservation of energy. The heat energy conveyed to the gas is transformed into internal energy, and a part of heat energy may go to work produced by the gas. So this is nothing more but a law of conservation of energy, or people say this is an equation of energy balance. So the change in internal energy and the work produced by the gas, all this may happen only due to some heat energy which is transferred to this gas volume. This is the energy balance equation, or the law of conservation of energy, or energy balance. Well, what about internal energy? The change in internal energy. Well, it's obvious, it's intuitively obvious that the internal energy should be proportional to temperature. And so if the internal energy changes, it means that molecules start moving faster. And it means the temperature has increased. So any change in internal energy should be proportional to the change in temperature. If I heat the gas, its temperature will be changed by delta T, and it means that the internal energy of the gas will also be changed, because the internal energy of an ideal gas, we speak about the ideal gases now, the internal energy of an ideal gas is actually a kinetic energy of the ideal gas molecules. If you have a system, a more complicated system, and not an ideal gas, but some other substance, maybe liquid or real gas or solid gas, then the change in internal energy will consist not only in the change of kinetic energy, but also in the change of potential energy of particles. Also, potential energy may change. But if we talk about the ideal gas, then the internal energy consists only of kinetic energy, because there is no potential energy of interaction, because in an ideal gas, molecules do not interact with each other. That is the definition of an ideal gas. A definition. There are no ideal gases in nature, but in many cases, a real gas behaves almost like an ideal gas. There are practically no interactions between molecules in many cases, especially when the gas is rarefied, when there are not many molecules per unit volume. So in this case, there are no interactions between molecules, and therefore we can neglect potential energy of interaction between molecules, and therefore the internal energy will consist only of kinetic energy of molecules. And so kinetic energy depends on temperature. Temperature depends on kinetic energy. So the larger the kinetic energy, the larger the temperature. And so the change in internal energy, delta U, will be proportional to the change of temperature, of gas temperature, delta T. Well, what we have stated so far, just the equation of energy balance and the intuitive understanding that the internal energy of the gas must be proportional, the change in internal energy must be proportional to the change in temperature of the ideal gas. That's all the information we need to answer the second problem, the second question in this problem. Indicate the stages or the sections of this process when the gas received or when it released heat. Heat energy, we mean, what is heat? Heat is this delta Q, that is heat energy. And so we must understand when the heat delta Q was conveyed to the gas and when the gas released some heat energy to the outside body. Well, let's consider process number 1. From point 1 to point 2. That is the first process. During this process, we discussed it. Volume, the gas volume, is proportional to the gas temperature, and pressure doesn't change. But temperature increases from T1 to T2. If the gas temperature increases, it means that delta T is positive. The temperature increases. The final temperature, T2, is larger than the initial temperature. So the delta T change in temperature is the final temperature minus initial temperature. And it will be positive for the process, for the first process we consider here. The change in temperature will be positive. Therefore, the first term here in this energy balance equation will be positive for the first process from point 1 to point 2. But in this process, also the volume, the gas volume changes. The gas volume increases from the initial value V1 to the final value V2. The gas volume increases. And we know that the work performed by the gas is defined by equation. We derived it last time. Gas pressure times change in volume, in gas volume. So if the gas is expanding, if its volume increases, like in the first process 1, 2, then the gas performs positive work because delta V is positive, like delta T is positive here. The gas performs some work when it's expanding, when the volume is increasing. So the gas performs some work during the first process 1, 2. The gas performs some positive work, and also the internal energy of the gas increases. So delta Q is positive. It must be given to this gas. Some energy must be given to the gas so that the gas could perform some work and the internal energy could be increased. So during process 1, 2, some external energy, which is heat energy, is given to the gas. And the direction of heat energy flow is from the outside bodies to the gas. From the outside bodies, like the fire of a candle, something like that, from any sort of heater, the energy should be given to the gas so that the gas temperature increases and the gas internal energy increases, and so that the volume should increase. The volume should increase under constant pressure in this first process. The volume increases, and therefore the work performed by the gas is also positive. So the gas needs some energy in order to perform work and in order to increase its internal energy. And this energy, in the form of a heat energy, should be given to the gas from outside bodies. The gas should be heated. So the energy flow during the first part of the process from point 1 to point 2 is directed towards the gas on this part. The heat energy should be given to the gas. What happens during other sections of the same process? For example, when the gas state changes from point 2 to point 3, when the state of the gas changes and the gas goes along this process, what happens here? We need to analyze the energy balance equation for this process. What happens with the heat energy? In this process, from point 2 to point 3, the gas temperature decreases. It goes down, and the volume remains constant. If volume remains constant, it means that delta V is 0 for the second section. Delta V is 0. It means that the gas performs no work during process 2-3, because volume is constant. And as volume is constant, then the change in volume is 0, and therefore the work performed should be 0. So the second term here is 0, while the first term should decrease because temperature is decreasing. Temperature here, when the gas state changes from point 2 to point 3, on this section, temperature decreases, and therefore the internal energy decreases, so that delta U is negative, and the second term is 0. Therefore, delta Q will be negative. It means that the gas should release some energy during this process. The heat energy should go from the gas to external bodies. The heat energy will go from this gas to external bodies. During process 2-3, and we show it here, some heat energy should go to external bodies, should be released by the gas. And then what happens during the process 3-1? Temperature is constant. Look here, temperature is constant. It means that the change in temperature is 0, and therefore change in internal energy is also 0, and therefore the first term here is 0. So only the second term may have its impact to this value of delta Q, the amount of heat energy transferred to or from the gas. Only internal energy may change. No work is only internal energy. Well, here the temperature is constant, and therefore delta U is 0. Delta U is 0, and therefore the first term is 0 in this process from point 3 to point 1. Temperature is constant here. Temperature is constant, and therefore PV is constant due to the equation of an ideal gas. So if temperature is constant, the first term does not change. Delta U is 0. The internal energy does not change. So the change of internal energy is 0. The first term is 0 on this process. And so we have to consider only the work performed by the gas in the process 3-1. What kind of work should be performed here? Work depends on the change of volume. And the volume here changes from point 3 to point 1. The volume is decreased. So the change of volume is negative. V1 minus V2 will be negative. Final volume minus initial volume. Final volume is V1 in this process from point 3 to point 1. Final volume is small, and initial volume was large. So final volume V1 minus initial volume V2 will be negative, and therefore the work performed by the gas will be negative. And as the first term is 0, then delta Q is negative. It means that the gas releases some heat energy to the outside body. The heat energy is transferred from the gas to the outside bodies. That is during process 3-1. The heat energy is transferred from the gas. So the gas performs its cyclic process from point 1 to point 2 to point 3. All these points reflect the state of the gas, and the the state of the gas changes in cyclic process. The state is repeated again and again after the gas moves along this curve. But the heat energy is transferred to the gas only during the first section of this process. We should convey some heat energy to the gas. And during all other, the remaining two processes, the remaining two sections, the heat energy is transferred from the gas and is given to the outside bodies. The gas releases heat energy during process 2, 3, 3, 2, and 3, 1. So the only process when the gas increases its heat energy is 1, 2. And in all other sections, the gas loses its heat energy. So that's the answer to the second question of this problem. Yes, the answer is here in these arrows. The answer is here. When the gas receives and when it releases heat energy. Yes, we have shown it, we have discussed it, and we have proven it. And you know how to find the answer to this problem. We have to find the answer to the first part of the problem, we have to analyze the gas equation. And in order to find answer to the second part of the problem, we have to analyze the energy balance equation. That's the way we solve this problem. Now I would like to discuss some important things related to this connection between the change in internal energy and change in temperature. If the gas temperature changes, then its internal energy changes. Obviously, there should be some coefficient of proportionality here. And obviously, I will have to use this equation in such a form that change in internal energy, if it's proportional to the change in temperature, then there is some coefficient of proportionality. Yes, delta U will be proportional to delta T, and this is the coefficient of proportionality. If delta T is small, the variation in temperature is small compared to the temperature itself, then this coefficient of proportionality most probably is constant. But if the temperature of the gas changes, or the temperature of any object changes, then this coefficient of proportionality may change. It may depend on temperature, and sometimes it does depend on temperature. But as far as the ideal gas is concerned and the problems which we consider here, this coefficient of proportionality is constant. That is the simple case of an ideal gas when C is constant for a small change of temperature. This coefficient of proportionality is called heat capacity. A heat capacity of a body. Any object has its own heat capacity. For example, you take any object like this one. In order to increase the temperature of this object by 1 degree, by 1 Kelvin, you need to increase its internal energy. It means that you need to supply some heat energy to this object. And the amount of heat energy will perform the amount of heat energy needed to increase the temperature by 1 Kelvin will be the heat capacity of this object. It's obvious that the heat capacity of any object depends on the volume of substance, on the amount of substance, on the mass of the object. If you take a small object, say 5 gram piece of chalk, you will need small energy to increase its internal energy and its temperature by 1 Kelvin. You will need a small amount of energy. But if you take a large object like a few kilograms instead of 5 grams, you will need much more energy to increase the temperature by 1 Kelvin. the temperature of this amount of matter. So this heat capacity is not very convenient because it depends on the mass of an object you are heating. You are trying to increase the temperature. So yes, it's possible to measure the heat capacity in experiment. It's possible to measure. How can you measure this heat capacity? Under the constant volume, under conditions of constant volume, when delta V is 0 and work is 0, when you can neglect the second term, under these conditions, the change in internal energy will be equal to the change of heat energy supplied to the gas. Heat energy supplied, yeah. And heat energy, actually, I made a small mistake here. It should be not the internal energy, but the amount of heat energy. The amount of heat energy here. So the amount of heat energy supplied, if you measure how much heat energy you need to supply to the object in order to increase its temperature by 1 Kelvin, then you will measure the heat capacity of this object. And the larger the mass of this object, the larger will be its heat capacity. This is physical quantity which can be measured experimentally, so this is quite reasonable quantity, but it's not very convenient because the heat capacity, because the amount of heat needed to increase the temperature of an object depends on the mass of the object. It's obvious. The larger the mass, the larger should be the amount of heat supplied to this object. So actually this equation is written in somewhat different form, as the amount of heat energy should be proportional to the mass of an object. We include mass here. So the mass will be here as a coefficient, and then this coefficient will be different. And I will denote this different coefficient by small letter c. Here was a capital C, and now I use small c. This is a different coefficient of proportionality. And also the mass of the body, and also change in its temperature. So this coefficient of proportionality now refers to a unit mass. Now, the physical sense of this small c is the amount of heat which is needed to increase the temperature of a unit mass of the body divided by temperature. So its units of measurement will be joules, that is the amount of heat energy, by kilograms by Kelvin. And this quantity is called a specific heat capacity. Or to be short, simply a specific heat. You may call it specific heat capacity or simply a specific heat. This small coefficient here refers to a heat capacity of 1 kilogram. And if your body, if you take an amount of substance larger than 1 kilogram, then you multiply this by m, and then the capital C, which was here, this is not G, this is capital C, will be equal, this coefficient, heat capacity, will be equal a specific heat times the mass of the body. Specific heat is actually heat capacity of a unit of mass of a body. Also, it's very often that people use another specific heat coefficient, another specific heat, which is referred to the mass of 1 gram mole. So this coefficient is also specific heat, but it refers to 1 mole. And its units of measurement will be joules to measure the heat energy, as any energy is measured in joules, and then Kelvin to measure the change in temperature, and 1 mole. what do we mean by 1 mole? Actually, it's a number of grams in 1 mole. So this coefficient is called, well, it's denoted by the same small letter c. And from the context, you can always distinguish between these two quantities. But it's also called a specific heat. But more often, it's called a molar specific heat. Molar specific heat. That is the amount of heat energy that should be transferred to a body of 1 mole of a body to increase its temperature by 1 Kelvin. Okay, after introducing the specific heat capacity, we can, I have to mention that there is another unit of measurement of specific heat, and actually heat energy, amount of heat energy conveyed to a body or exchanged between bodies. There is another unit, a non-system unit, which is not a part of the international system of units, but which is very frequently used, very often used in actual calculations and laboratory experiments. That is the amount of heat energy that is usually measured in joules, but very often it's measured in calories. So that 1 calorie is 4.18 joules. And therefore, for this purpose, the specific heat sometimes is measured not in joules per kilogram, not in joules per mole, but in calories per mole. Sometimes you will encounter such unit of measurement, calories per mole Kelvin, for the specific heat capacity. Well, why calories are useful and convenient in experimental physics and in laboratory measurements? Because heat capacity of water is 1 calorie per gram. So if you need to increase the temperature of 1 gram of water, which is 1 milliliter of water, by 1 degree Kelvin, then you will need 1 calorie of energy, 4.18 joules. That is to increase the temperature of 1 milliliter of water by 1 Kelvin. Now we will have a 5-minute interval. Okay, we continue after this short interval, and in order to illustrate how this physical quantity of a specific heat, can be used, I will consider a small problem. Assume we have some liquid in a vessel. There is some liquid here, and the mass of the liquid is m1, and the temperature of this liquid is T1, absolute temperature. And imagine we take some other liquid and pour it into this. We pour some other liquid into this vessel, so that we take some other liquid of mass m2 and temperature T2. If these two liquids are the same, like water and water, then it will have the same physical parameters and the same specific heat capacity. But if liquids are different, then they will have different heat capacities. For example, this liquid may have heat capacity C1, and this liquid may have heat capacity C2. So if these are different liquids, chemically different, then they will have different constants, different heat capacities, or specific heat capacities. So the question is, if we pour this amount of liquid into the vessel and allow for these liquids to mix, then what will be the final temperature of mixture? What will be the final temperature after the temperature is stabilized, after it's fixed, and after the two liquids have mixed together? So what will be the final temperature? That is the question in this problem. We have to find the final temperature of this mixture. Certainly, we assume that there is no heat exchange between these two bodies and the outside bodies. No heat exchange between the surrounding bodies and this heat, and this liquid. It means that the walls of this vessel are thick and heat insulating. No heat exchange with the external bodies, and so also no heat exchange through this surface. It means that this vessel must be closed with some lid above it, so that to exclude any heat exchange with surrounding bodies. So we consider only the heat exchange between these two liquids. Suppose temperature T2 is larger than temperature T1. So this is the hot liquid and this is the cold liquid. In this case, it's obvious that this liquid, the second liquid which is being poured into the vessel, will cool down to some final temperature, and the liquid in the vessel will have to increase its temperature. It will have to be heated up to the final temperature Tf. When this liquid changes, when any liquid changes its temperature, it will change its internal energy. Actually, when temperature is changed, the liquid will either release some heat energy or absorb some heat energy. If the temperature is increased, then delta T is positive, and the liquid will have to absorb some heat energy from the surrounding bodies, from another liquid. But if the change in temperature is negative, that is, when temperature falls, when temperature is reduced, then delta T will be negative. Then the heat energy will be released by the cooling substance. And we must use the energy balance to solve this problem. So how much energy, I mean heat energy, will be released when the hot liquid is cooled down to its final temperature Tf, which is unknown? we have to take the specific heat capacity of the second liquid, multiply by the mass of the second liquid, and by change in temperature, the initial temperature T2 minus final temperature. That amount of heat will be released by the second liquid. And this very amount of liquid, this very amount of heat energy will be absorbed by the first liquid. And the amount of energy needed for the first liquid to increase its temperature from T1 to Tf will be the heat capacity of the first liquid, its mass, and the change in temperatures, the final temperature, Tf minus initial temperature of this first liquid. It's obvious that the first liquid, whose original temperature was T1, must be heated somewhat to increase its temperature to some final temperature. So this difference in temperatures will be positive. Tf final temperature is larger than the initial temperature. And here I take the difference as initial temperature minus final, because I know beforehand that final temperature will be smaller than the initial temperature, because the second liquid will have to cool down to some intermediate temperature between these two temperatures. So according to energy balance, we know that the conservation of energy, law of conservation of energy, says that the energy cannot be created and cannot be lost. It's conserved. And if this system is placed in such a condition that no energy can flow in from outside bodies and no energy can flow to the outside bodies, so there is no energy exchange, no heat exchange between this system of liquids and the outside bodies, then the total heat energy inside this system must remain constant. It means that the amount of energy lost by second liquid must be equal to the amount of energy received by the second liquid. So the energy balance in this case will be delta Q1 equals delta Q2. The energy lost, the heat energy lost by the second liquid should be equal to the heat energy, the amount of heat energy acquired or absorbed by the first liquid. Well, using these expressions, we might simply state that C1M1, I'm using this expression, final temperature minus initial temperature, should equal to C2M2, and here is initial temperature minus final temperature. Both quantities are positive because I use this such a order of these terms that this expression in round brackets is positive here, and also it's positive here. So this is okay to use such an equation. We have to find the unknown quantity, which is final temperature from this equation. So in order to find final temperature, I have to take all the terms containing Tf to one part of equation. So C1M1 plus C2M2 multiplied by final temperature, this one C2M2, will be equal to all terms which don't contain the final temperature. That will be C2M2 T2 plus C1M1 T1. So that final temperature of the mixture of two liquids will be given by C1M1 T1 plus C2M2 T2 divided by C1M1 plus C2, M2. That is the answer to the problem stated. The final temperature of the mixture of two liquids will be given by this formula. As always, we have to, as we always do, we have to check this formula for correctness. If it's correct, first of all, we check the units of measurement here. The units of measurement in the nominator will be the units of heat, specific heat, times mass, times kilograms, times Kelvin, which is temperature. And the units of measurement in denominator will be specific heat times mass times kilograms. So the units of measurement for specific heat will cancel, and the units of measurement of the mass will cancel. And the only units remaining will be Kelvin here in this formula. That's exactly what we need. We need kelvins to measure the final temperatures. So the units of measurements are correct. Why do we have to check the final formula for the units of measurement? Because should we make any mistake in our calculations, the units of measurement in the final formula most probably will be broken. Most probably the units will be incorrect if we make some mistake. So when we check the units of measurement in the final formula, we actually check the correctness of our calculations. But sometimes the mistake can be made in such mistake that the units of measurement will not be changed. Sometimes the units of measurements are correct, but the formula will be incorrect. Yes, is it possible to make such a mistake? Certainly. For example, if I miss the sign somewhere and take the sign here, this is incorrect. But it's quite possible to make such a mistake. I just analyze the possible mistake. This is a mistake. This is incorrect. But it's quite possible to make such a mistake. How can we check the final formula for such mistake? We have to analyze the formula for physical sense, if it's reasonable or not. So imagine that we take the same liquid so that C1 equals C2, the same liquid with the same specific heat, and the same mass of liquids, the same mass, M1 equals M2. Then we will have here in the nominator, I will show it, specific heat and mass, which is the same, and T1 minus T2. And suppose that T2 is larger than T1, then this expression will be negative, and we will obtain for the final temperature negative number. But this is temperature in kelvins. In Kelvin, degrees of Kelvin, it cannot be negative. It must be positive, always above zero, always. So if it's possible to obtain, if it turns out that the formula can give you negative temperature, then this formula is incorrect for sure. And we must check our calculations in order to find the mistake. And if we have done this mistake, we must correct it and find the correct formula, which will never give you a negative temperature. So in this way, we have to analyze any solution we obtain. A solution to any problem, we have to analyze it for physical sense, if it's reasonable, if the formula is reasonable, if it gives you a reasonable result in any situation. Yes, if you change some parameters here, allow some parameter to go to zero, some parameters to increase, and some parameters to decrease, what will give you this formula if it's reasonable? That such a check is always necessary in order to make sure that you have obtained correct formula. So if we take similar liquids, for example, water and water, then heat capacity will be the same. C1 will be equal to C2, and C1 and C2 will be the same coefficient. So in this particular case, when we have similar liquids, the formula will turn into a different expression when heat capacity is cancelled, and we will obtain M1 T1 plus M2 T2 divided by M1 plus M2. So if if two liquids are identical, if two liquids are similar, chemically identical, then the heat capacity will be the same, and this coefficient will cancel from this formula, and we will obtain a simplified expression, more simple, which includes only the masses and temperatures. And also suppose we use equal masses. We use M1 equal to M2, equal amounts of liquid, equal masses of liquids. Then M1 will be equal to M2, and all this formula in this case will be given as the sum of temperatures divided by 2. The sum of temperatures divided by 2. So if we have equal amounts of similar liquids, like water here and water here, and we take like 100 grams of water and 100 grams of water which we add of different temperature, then the final temperature will be given like a mean temperature, a mean between these two temperatures. Mean means that if T equals in Celsius 10 degrees Celsius, and this is 30 degrees, then the mean will be 20. The final temperature will be 20 degrees. If you take equal amounts of water, the first amount of 10 degrees Celsius and the second amount of water 30 degrees, then the final mixture will have 20 degrees. That is the simplest case when masses are equal. But if masses are not equal, you have to use this formula. And if liquids are different, having different heat capacities, or specific heat coefficients, then the more general formula will be this one. So this is the way we can use a heat balance equation, heat balance, or energy balance. That's the same, because when we say heat, we mean heat energy. Heat balance is the heat energy balance, or the energy balance. That's the same. That is, we use the law of conservation of energy here, the law of conservation of energy. And then we can calculate the final temperature of mixture of two or more components. You may take more than two components. You may take 3 or 4 or 5, etc. components all mixed together with different masses and different temperatures. Then such a formula will give you the result. If you have more than two components, then here you will have, it's easy to establish that you will have more terms of similar structure. So if there are 3 components, then the formula will have, then you will have the answer in this form. If you have 3 different liquids of masses M1, M2, and M3, and all liquids are different and they have different specific heat coefficients, then the final temperature of the mixture of 3 different components will be given by this formula. It's easy to establish from the heat balance equation. I would like to discuss now this quantity of specific heat. Specific heat capacity, a coefficient of specific heat capacity. So by definition, specific heat for any object, be it an ideal gas or some amount of water or solid body or anything, specific heat, by definition, is the amount of heat energy needed to increase the temperature by 1 degree. If you insert here in this formula 1 degree of Kelvin, or 1 Kelvin, then numerically the specific heat capacity will depend on the amount of heat needed. So if we take the quantity of substance like 1 mole, then that will be the specific heat for 1 mole. Specific heat for 1 mole. And I will consider 1 mole from now on. It's convenient to deal with moles because I remind you that 1 mole of any substance contains the same number of molecules, which is the Avogadro constant, about 6 times 10 to the power of 23 particles. That is the Avogadro constant. That is the number of molecules in a single mode about. That is the number of particles in a mole. So this is dimensionless number, but actually the meaning is number of particles per mole of any substance. If you take 1 mole of hydrogen, a gas hydrogen has formula H2, then the atomic weight of the molecule is 2, and so the mole of a hydrogen will be 2 grams of hydrogen, 2 grams. If you take an oxygen, gas oxygen, O2, then the atomic weight of this molecule will be 32, because atomic weight of 1 atom of oxygen is 16. Then that atomic weight of this molecule will be 32, approximately. It's rounded up to 32. So 32 grams of oxygen will constitute 1 mole, and the number of particles will be the same as in 2 grams of hydrogen. So 2 grams of hydrogen contain the same number of molecules as 32 grams of oxygen, and the number of molecules in 1 mole is given by an Avogadro constant. And so I will consider the amount of substance as 1 mole for any substance, and I will consider the molar heat capacity. Molar heat capacity, that is a specific heat capacity referred to 1 mole here. So if we have this definition of a heat capacity, then we can use the energy balance equation, which I have already written here, the energy balance for an ideal gas, which relates the amount of heat transferred to the gas with the change in internal energy and work produced by this gas. This is the energy balance equation, and in thermodynamics this equation plays an important role, and it's called the first law of thermodynamics. That is the first law of thermodynamics. There is the second law and the third law, but first we consider the first law of thermodynamics, which is an energy balance equation. So if specific heat capacity by definition is such a formula, then we can write that specific heat capacity by definition being delta Q divided by delta T, which is temperature. And using this expression for delta Q, I will have delta U by delta T plus the work produced by an ideal gas by delta T. So this equation will give us different results for different processes. We know that the work delta A by definition is pressure times change in volume. And suppose change in volume is 0. That is, the process considered goes under constant volume. So we consider the process under constant volume. It means that delta V is 0 and the work produced by the gas is 0. So in this particular case, the heat capacity, the molar heat capacity, will be equal to the first term only, delta U times delta T. And such heat capacity will refer only to change of internal energy under constant volume. To underline that this is a heat capacity under the condition of constant volume, such a quantity is denoted by CV with the index V here to underline that this is the heat capacity under the constant volume when volume is not changed, and therefore work is not produced, and therefore this term will be 0, and therefore in this energy balance equation we will have delta Q equal just to the first term here, and the first term will be equal to constant heat capacity delta T. That is under conditions of constant volume. Now let's consider conditions under constant pressure. What means if pressure is constant? Then the heat capacity of gas is denoted by Cp, which is heat capacity under constant pressure, and that will be given again by the same formula under constant pressure. To underline that we take this expression under constant pressure, we denote it by such a symbol. I introduce such a notation which you will encounter in the literature. Change of amount of heat energy divided by change in temperature under the conditions of constant pressure. That's the meaning of such notation. And so that will give us the heat capacity under constant pressure. So under constant pressure, volume is changed, and therefore work is produced by the gas. And therefore, in this first law of thermodynamics, I will have to consider both the first term and the second term in this equation. The first term will be delta U, and the second term will be delta A, which is non-zero now, non-zero, divided by delta T under conditions of constant pressure. What is delta U divided by delta T if internal energy changes when temperature changes by a small amount of delta T? This coefficient is denoted by CV. So the first coefficient here, delta U divided by delta T, is already known to us. This first coefficient under the this first coefficient is CV. That is the heat capacity under constant volume. And the second term here, the first term is CV, and the second term must be assessed using what we know. And we know the gas equation, and we know the definition of work, that work is P delta V. So if pressure is constant, and we consider this situation when pressure is constant, then the change in volume will be proportional to the change in temperature. And the change in volume can be expressed in this particular case as the change in volume will be R delta T divided by pressure. And so from these two equations, we immediately obtain that the work produced is pressure times delta V, but delta V is given by this expression. When we substitute all these expressions into, when we substitute delta V here, we will find pressure cancelled, and the work produced will be R delta T. And pressure here and here will cancel. So the work produced under such conditions of constant pressure may be substituted here in this equation, and we will obtain finally the first term equal to CV, the heat capacity, molar heat capacity under the constant volume. And if we substitute this expression R delta T here for delta A and divide by delta T, we will see that delta T cancels, and what remains here is the universal gas constant. So I considered the gas equation for single mole. It means that all the quantities, all the physical parameters of this amount of ideal gas will refer to 1 mole. And therefore, I told you that I consider the molar capacity, that is the heat capacity of the gas taken in the amount of 1 mole. That is like 2 grams of hydrogen or 32 grams of oxygen, etc. We take 1 mole of any substance and obtain heat capacity, and we discover that heat capacity under different conditions will be different. Actually, we obtained here the relationship between heat capacities of an ideal gas in the conditions of constant pressure, which is equal to heat capacity under constant volume plus universal gas constant. Such an equation, such a relationship between heat capacities, molar heat capacities of an ideal gas, is called a Robert-Meyer formula, a Robert-Meyer expression. Well, this is a Robert-Meyer formula, a relationship between molar heat capacities of an ideal gas taken under constant pressure, this one, and under constant volume. This is a Robert-Meyer formula. What about other processes? We have considered a process under constant volume and a process under constant pressure. What about other possibilities? If we take, for example, a process under constant temperature, then change in temperature will be 0. And then, by definition, the heat capacity is delta Q divided by delta T. Heat capacity under constant temperature will be given by the same formula, because this is the definition. But in this case, delta T is 0. What does it mean that 0 is in denominator? It means that whatever quantity delta Q you divide by 0, you obtain an infinite number. Yes, that's it. You obtain an infinite number. So heat capacity under the conditions of constant temperature is infinite for an ideal gas. And if the gas receives some heat energy, then delta Q is positive, and you will obtain plus infinite quantity here. And if the gas releases some heat energy, then delta Q will be negative, and you will obtain minus infinite quantity here. So actually, if the gas process is not exactly isothermic, not exactly the temperature is constant, but approximately constant. However, small changes in temperature may occur. then this number here, delta T, will be very small, not exactly 0, but very small, as it usually the case. It's impossible to ensure that the temperature is almost constant. It's impossible to ensure. Always there will be some small variations in temperature which cannot be controlled, like some thousandths of millionths part of a Kelvin. Practically, you cannot control such a small variations in temperature. Actually, in reality, you will always have some very small number here if you want to sustain temperature constant. Actually, it will not be absolutely constant. It will be approximately constant. So there will be small variation of temperature here. And so here you will obtain large number, which is certainly not the infinity, which is very large number, but finite number. There are no infinities in nature. Infinities may occur only mathematically, but practically you will always obtain a finite number, but very large, very large, actually unlimited. The better you sustain the temperature constant, the better are the conditions of the experiment, the larger will be the number here. So it may be very large, but it will always be finite, actually. So the heat capacity of an ideal gas and of any object under such conditions will be, well, we say infinite, but practically this is very large number, certainly, but finite. What about, I would also like to mention an adiabatic process. What is adiabatic process? We imagine a gas in a cylinder under a piston. So here we have some gas. It has some volume and some pressure and some temperature, all the parameters needed to describe the state of the gas. And consider such a situation when the walls of this cylinder, the walls are thick, very thick walls. And this material is heat insulating material, so that the heat cannot penetrate and cannot go through the walls of this cylinder. Such a cylinder, such a vessel is called an adiabatic vessel. And the gas in such a vessel is in adiabatic conditions. The word adiabatic means adiabatic conditions and adiabatic process means that there is no heat exchange with the surrounding bodies. No heat exchange. What happens in this case? If there is no heat exchange, if the walls are impermeable for heat, then delta Q will be 0, and the heat capacity under adiabatic conditions will be 0 divided by delta T. Is it possible to change temperature in such a gas? Certainly. We can compress the gas by moving the piston down. We can reduce the volume, and in this case the temperature will increase. And we can expand the gas by moving the piston up, and in expanding the temperature will be dropped, it will be decreased. So the temperature can be changed by a finite quantity. But no heat exchange means that the amount of heat energy transferred to the gas is 0, or taken from the gas to the outside bodies is 0. So if this is 0, then the heat capacity, the specific heat capacity will be 0. In adiabatic condition, the heat capacity will be 0. So discussing the heat capacity, we discover that this quantity defined by this equation, the specific heat capacity defined by this equation, can take practically any magnitude, any value between plus and minus infinity. It may be 0 in some processes, like in adiabatic process. It may have some finite quantities related between each other in such a way that established by Robert Meyer, or it can be very large number, like almost infinity. So the heat capacity may take any value. Actually, in different processes, it's different. That's what was important to tell about the heat capacity, specific heat capacity of different substances in different processes. On this point, let us finish this lecture and see you on Friday. Goodbye.